This is Graduate Model Academic Enhancement School GMAT 41. You are welcome to our basic physical chemistry class. In this video, we're going to look at Dalton's law of partial pressure on the gas laws. Now, I'm talking about Dalton's law. What does that law state? We have it on the board here. It states that at constant temperature, the total pressure exerted by a mixture of gases is equal to what? The sum of the partial pressures of the component gases, provided that the gases do not react chemically. What does that law mean? I'm going to use this marker and my magnet to represent gases. And now let's assume that you have these as gases and you mix them. Now these gases cannot react chemically, that's the condition there. Now I'm keeping the temperature constant. These gases are confined in a given volume, which means, of course, you know, they assume the volume of the container, alright? It means that they have the same volume, the same temperature. But of course, the number of moles, that is the quantity of the gases in the mixture, different. According to Dalton, to get the total pressure of this gas mixture is equal to the pressure contributed by this gas, the pressure contributed by this gas, the pressure contributed by this gas, you add them together. That's just the point. Now, from that statement, we can actually work out or write a mathematical expression for it that total pressure is equal to P1 plus P2 plus P3 plus down to plus Pn, depending on the number of gases that are found in that mixture. Now, we can write a summation term for these. That total pressure is equal to summation Pi, where I represent all this number of gases, 1, 2, 3, and the rest. So I taking from gas 1 down to gas n, that is depending on the number of gases you have there. P here represents total pressure exerted by the gas mixture, and then Pi represents what? The partial pressure of the individual gas. Now we know that pressure, as we derived from our previous class, is that P is equal to nRT over what? V. Do you remember the ideal gas equation? Good. It simply means we can write each of these pressures here, P1, P2, P3, down to Pn, in terms of nRT over V. We are going to take a short break. When we come back, we'll explain these concepts and the importance of this equation to this particular quantity, Ni over Nt. You are welcome from our short break. Before the break, we established this fact, and we said that from Dalton's law, knowing that the ideal gas equation is given as nRT over V, we can write the partial pressures of each of the component gas in terms of its number of moles, in terms of universal gas constant R, in terms of temperature and the volume. And so that's what we want to do. We're going to rewrite these pressures in terms of the number of moles, R, T, and V. So if we want to write for P1, look at it. It's going to be equal to N1. Remember that the number of moles of the gas mixtures are different, is that not so? So we're going to be N1 times RT over V. Did you take note that R is constant? T is also constant because here the gas is confined in a given volume and you're channeling an absolute temperature to it. It's just like when you have a pot on fire and then the fire is heating up. Since the temperature is coming from one source and the source is what? The fire, it means that we take it as absolute temperature, which is the same for all the gases. And of course, the volume is also the same because they are in the same container as a mixture. We can write P2 in that form, look at it as well, to P3 in that form, and then Pn in that form. So you notice that the only difference here is the number of moles. That's the quantity of the gas. Alright, now having written this, what if we decide to divide each of the partial pressures by the total number of pressure? Watch what we're going to get. I'll come here and divide P1 over total number of pressure, which means I'll have N1 RT divided by V divided by, look at it, NT RT over V, where this NT represents the total number of moles. That is, when you add all the number of moles of the gases. Remember, we are writing pressure in terms of nRT over V. Is that okay? Now, that being the case, please watch this part carefully. Did you notice that since RTV, that is RT over V, they are the same, it means they will cancel out from this equation. Are you saying that right? Therefore, P1 over P will now become equal to N1 over NT. That is number of moles of gas 1 divided by the total number of what moles. Watch this thing please. If you make P1 subject to the formula, for example from here, P1 over P equal to N1 over NT. Of course, you agree with me to be P1 equal to N1 over NT times total pressure, because you're going to cross multiply. Alright, following what I explained here, it's similar for P2 over P, you're going to get N2 over NT, and then down to that of Pn over P equal to Nn over Nt. Now, with this thing we got, what do we want to do now? You know that for all the gases, you can simply refer to it as what? Pi, the partial pressure. So, it simply means that Pi, that is partial pressure of the ith component, a particular gas, divided by total pressure, will be number of moles of that ith component divided by what? The total number of moles. And if I make Pi subject to the formula, I'll cross multiply to the Ni over Nt times total pressure. Look at it. So you see, this simply means that the partial pressure of a gas is equal to the number of moles of that gas divided by total number of moles times total pressure. This quantity Ni over Nt is called the mole fraction. In the next video, we're going to explain that important quantity that we encounter in basic physical chemistry, mole fraction. Alright, now we want to talk about mole fraction. You would recall in the previous video we established the fact that partial pressure of any component gas in a gas mixture, according to Dalton's law, when we worked around that, is equal to number of moles of that particular gas divided by what? Total number of moles. That is summation of all the gas number of moles times the total pressure. And now we stated that Ni over Nt is our mole fraction. So look at the definition. The mole fraction of any gas is the number of moles of that gas divided by the total number of moles of all the gases in the mixture. It simply means that in place of Ni over Nt, we can put Xi. Yes, because it's equal to Xi, the mole fraction. Therefore, following Dalton's law, we can say that partial pressure of any gas component is equal to mole fraction of that gas times the total pressure. Therefore, if you are talking about partial pressure of gas 1, look at it, it will be mole fraction of gas 1 times total pressure. Partial pressure of gas 2 equal to mole fraction of gas 2 times total pressure. And partial pressure of gas 3 equal to mole fraction of gas 3 times what? Total pressure. Now the meaning of all the terms we used here is written on the board here. You can go through that. I simply represent a particular gas in that mixture, so we'll refer to it as the ith component gas. There is a law that is very similar to Dalton's law. It's a corollary to Dalton's law. It's called the Amagat's law. Look at it, Amagat's law. Refer to it as Amagat's law of partial volume. So everything we did under Dalton's law also applies to that. And that is why the partial volume of any gas in a gas mixture is equal to mole fraction of that gas times the total volume. Alright? So refer to that as Amagat's law. Let us quickly establish something, that summation of all mole fraction is equal to unity. That is 1. Let's establish that, alright? Are we together? Okay, let's do that. Now we know that according to Dalton's law, total pressure is P1 plus P2 plus, okay, I'm going to limit it to 3 components, alright? So let's just go there. Besides, much of the things we're going to treat will be binary solution or trinary solution, as the case is. Alright, now for this P, we are going to write equal to P1, I will substitute X1 times total pressure for it, plus P2, I will substitute mole fraction 2 times total pressure, and then P3 will be mole fraction 3 times what? Total pressure. Now you notice that if I have P, it will be equal to X1 plus X2 plus X3, and then everything in bracket times total pressure. Please look at this equation. We can divide through by total pressure, is that not so? And if you divide through by total pressure, here will be P over P equal to X1 plus X2 plus X3 in brackets times P over what? P. Alright, what's going to happen? You know that the total pressure will cancel out from here. This will give us 1, is that not so? Therefore, we have 1 equal to X1 plus X2 plus X3. Please take note of this equation 5. I'm going to start it. What does it mean? That if you add all mole fraction of a given gas component in a mixture, you will get what? 1. Of course, mole fraction can also be converted into a percentage as well too by multiplying it by 100. Please take note of this. Sum of all mole fraction is equal to what? 1, that is unity. Oh yeah, now that we have our first question on the board, and then the question says, what is the mass of oxygen that can be stored at 15 degrees centigrade and 1 atmosphere in a cylinder with a volume of 40 liters? Now, how do we solve this problem? Please, be it physics, be it chemistry, or even any other calculation course, when a question is given to you as a strategy, the first thing you should do so as to quickly help you remember the formula to use. The first thing you need to do is to bring out the data, what you know from the question and what you're looking for. Now, if you look at this problem, we have to calculate the mass of oxygen that will be stored under that condition. We don't know that. The temperature is what? 15 degrees centigrade or Celsius. You would recall that you were told in our previous video that you need to convert it to kelvins by adding 273. If you do that, 15 plus 273 will give us 288 Kelvin. And now the volume given to us, the volume is 40 liters. The pressure is 1 atmosphere. Now if you look at this data given to us, we have temperature, pressure, volume. We are asked to find mass. I hope you know that mass is also related to number of moles using this formula. We have number of moles equal to mass over molar mass. Is that not so? Which simply means, because of this data given to me, that the formula to use in solving this problem is the ideal gas equation, PV equal to nRT. And then we know that N is equal to mass over molar mass, then RT. You see that right? Now, this is what we're looking for, this mass, the small letter n. So if we do some substitution here, pressure is in ATM, which is 1 ATM. Volume is 40 liters equal to the mass, we don't know. Molar mass of oxygen is what? 32 grams per mole. How did we get that 32? Now you listen, the relative atomic mass of oxygen is 16. Now when you're talking about oxygen gas, because this is a gas, molecular oxygen, are you getting me? It's O2. So you're going to multiply 16 by 2 to get 32. So I'll come here and write 32. I am going to divide that 32 by 1000. What is the reason? To convert from grams to SI units of mass, which is kilogram. You know, to convert from gram to kilogram, you divide the gram value by 1000. That 32 is in grams, take note. Then multiply by the value of R. Which value of R will I use here? Good. This is another important thing coming into play. Okay? So this course is a course you want to take it very seriously. The value of R you use, if you recall from our previous video, I told you that it depends on the unit of pressure and what? Volume. Now in this problem, the unit of pressure is ATM, atmosphere, and volume is in liters. Therefore, the value of R to use is 0.082057. That one that is in liters atmosphere per Kelvin per mole. You can check through from your previous video. Then multiply by temperature 288. If you work around this, make that mass subject to the formula. You're going to do 40 times 0.032. Anything you get, divide it by the product of these two terms to get this mass. If you do that, of course, working through that, good, it's giving me 0.054 kilogram. Therefore, this is the mass of oxygen stored under this condition. Our third question on the board here, 1 liter container at 25 degrees centigrade contains 12.0 gram nitrogen gas, that N2 is nitrogen gas, 0.4 grams hydrogen gas, H2, and 8.0 gram of oxygen gas, O2. Calculate the mole fraction of nitrogen gas. Now you know that mole fraction is simply the number of moles of that gas divided by the total number of moles of the component gases or the constituent gas. For this problem, what do we know? The volume was given to us to be equal to 1 liter. The temperature was given to be 25 degrees centigrade. I'm not going to convert anything here because the problem we have to solve here has nothing to do with temperature and volume as it stands. It only has something to do with the masses given to us. Remembering that mass can be converted to what? Number of moles by dividing that mass by molar mass of the gas. And so I will just focus on this. For nitrogen gas, the number of moles of nitrogen gas, let me say the N2, that is number of moles of nitrogen gas, is going to be mass of nitrogen, which is 12 there, divided by what? The molar mass of nitrogen, or molecular weight of nitrogen. Relative atomic mass of nitrogen is 14. That is N2 there, so you multiply it by 2 to get 28. There is no need of converting anything to kilogram by dividing by 1000 because here the mass given to us in question is in grams. This 28 molecular weight of nitrogen is also in grams per mole. Is that okay? So you just leave it that way. Divide by, let us see, okay, you punch your calculator, 12 divided by 28 is giving me 0.4286 to 4 decimals, alright, for accurate result. We're going to do same for the other. We're going to have a number of moles of hydrogen gas is going to be 0.4 divided by molecular weight of hydrogen is 2. Relative atomic mass is 1 times the atomicity here you're going to get. So if you do this, you get 0.2. This is mole. This is mole. Then similarly, you do for oxygen gas. The mass of oxygen is 8 divided by 32, the molecular weight. If you do 8 divided by 32, what will you get? 8 over 32 is giving us 0.25. The terminating decimal stops there. So we've gotten the number of moles. We are now to calculate the number of, that is the mole fraction of nitrogen gas. That's what the question is based on, we don't know. Now you recall that mole fraction of any component is going to be number of moles of that component divided by N total. And so the mole fraction of nitrogen gas is going to be number of moles of nitrogen, which is 0.4286 divided by sum of the number of moles. So we're going to add 0.4286 plus 0.2 plus 0.25. Does that make sense? And so if you walk around that, what will you get? Let's find out. So 0.4286 divided by the addition of the denominator. So you're going to open brackets like this and before you add. So 0.4286 plus 0.2 plus 0.25. Alright, it's giving me the mole fraction to be 0.487. Mole fraction does not have units because it's a ratio of moles, alright? It's a dimensionless quantity. So this is the mole fraction of nitrogen gas in that problem.